So first of all, thank you to GCC and thank you to everyone who came and all my fellow presenters. So my name is Catherine Wilka. I work with Susan Solomon at MIT. I study a variety of issues around the intersections of ozone depletion and climate change. This one's mainly going to be focused on trends, long-term trends in ozone depletion, and I'm going to start with a bit of motivation, mainly because I know atmospheric chemistry is a class that probably very few of us in this room have taken, since it's a bit of a niche. But most people know ozone shields the Earth against UV. Oops, it's back. Where's the? Oh, the top.
You have to look at the sun first.
Ah, excellent. Thank you. So, and what's key about this diagram is it shows that this is the really high energy UV light, UVC and UVB. These ones are the ones that cause skin cancer, particularly melanoma. They cause cataracts. They cause crop damage. We do not want these things at the surface. They're very efficiently blocked by the ozone layer. And in the absence of anthropogenic ozone depletion, stratospheric ozone levels are naturally set by a balance between multiple different chemical cycles. And that, however, changed about the middle of last century when we started emitting large quantities of molecules called chlorofluorocarbons, or CFCs. Now, these chemicals, which were used for everything from aerosols for 80s hair and to refrigerants in your refrigerators to cleaning solvents for computing chips, they were considered these really awesome chemicals because they were so stable, unlike previous ones which had a tendency to poison you or explode. So these were great, but the problem is that because they're so stable, they have really long lifetimes in the troposphere, and they can be transported all the way up into the stratosphere, where they then deposit much more chlorine and bromine than naturally occurs there. So, a very fast overview of ozone depleting chemistry. You don't have to get into all of these reactions over here, but basically, chlorine destroys ozone through gas phase catalytic cycles, and that means that every chlorine molecule is not used up in this reaction. It can be used again and again to destroy multiple ozone molecules. So for this talk, I divide chlorine into the active forms of chlorine, that's ClO and Cl. Those are the ones that are capable of interacting in these cycles. You can see ClO here, Cl here. They are the ones that directly destroy ozone. There are also reservoir species, like chlorine nitrate and hydrochloric acid, which by themselves cannot destroy ozone. However, these reservoir species, which are what most of the chlorine in the stratosphere is in the form of, can get partitioned into the active form by reactions on the surfaces of particles and aerosols, which we call heterogeneous reactions. And these are some of the main ones I'm looking at. So you can see the blue ones are more of a light lavender on this presentation, but they're reservoir forms. These don't hurt ozone by themselves. The red ones, however, once they are in that form, they can be photolyzed by UV, the same stuff that ozone is blocking, and then you have these active chlorine molecules that can destroy ozone very, very fast. So, a few decades ago now, scientists discovered the ozone hole. And that is, this is not a true hole in that there is still some ozone even at the center, but it is an almost total depletion at some altitudes of the ozone layer that forms in the Antarctic spring, which is September, October, November in the southern hemisphere. And it forms there because on PSCs, which are polar stratospheric clouds. So these clouds provide these surfaces that I was talking about for the reservoir species of chlorine to be partitioned into active ones. Now, in order for this to happen, you need chlorine, obviously. You also need sunlight because you need it to photolyze. That's why it doesn't happen until the spring. It's because during the long Antarctic night, you don't have any sunlight, so this chlorine just builds up and builds up and builds up until the sunlight hits it in spring, and then all these destructive cycles start. These cycles are also extremely temperature dependent. They're very nonlinear. With temperature, the efficiencies jump by about 6 orders of magnitudes within 5 to 10 degrees. So you need very cold temperatures, and just a few degrees can be the difference between a very large ozone hole and almost no ozone hole at all in a given year. So PSC, polar stratospheric clouds, they can be formed of water ice. They can be formed of these compounds called nitric acid dihydrides, or a combination of nitric acid, water ice, and sulfur. That's what happens in the Antarctic. This stuff also happens outside the Antarctic. This can happen on pure SO2 liquid aerosols, and one major source of that is from volcanoes. So we've known for a long time that mid-latitude depletion is enhanced after large volcanic eruptions, because you get so much more sulfuric acid into the stratosphere, and because of the slow circulation that was mentioned in the preliminary talk, there's very long residence times of these aerosols, on the order of 1 to 2 years once they're up there. So there's also some recent work out of my group that's showed how this can happen in the tropics under specific conditions as well, especially in the monsoonal regions. So then, given all this chemistry that we know, one of the main questions in atmospheric science over the last decade is, when are we going to see ozone recovery? We passed the Montreal Protocol, which banned CFCs, that lowered the amount of chlorine in the stratosphere. We can measure that the amount of chlorine in the stratosphere is going down. So at some point, we should be able to see the ozone layer start to recover. But there's a lot of natural variability in the ozone layer, just like in most parts of the atmospheric cycles. So we are looking in this study at the impact that moderate-sized volcanic eruptions, not just the giant ones like Mount Pinatubo that everyone kind of knows about and sort of made the news, but somewhat smaller ones that are maybe an order of magnitude smaller. So how much did these impact ozone? So to do this, I use the SD-WACM model, which I'm not going to get into the details of here, but you're more than welcome to come talk to me afterwards if you want to talk shop on modeling. It's basically a model that's commonly used to look at the upper atmosphere, stratosphere, mesosphere is a version that goes up to the thermosphere. And we can run it in modes that use reanalysis meteorological fields, so this is nudging it to the best guess of what the atmosphere is actually doing at that time. And the key thing for this project is that we were able to turn off those heterogeneous chemical reactions I talked about earlier, so we were looking at gas-phase chemistry only. We were also able to, in a separate run, remove volcanic aerosols. So our main run has this data set of moderate and large volcanic eruptions. We can take that out. We can say how much heterogeneous chemistry is happening on background aerosols alone. So when we do that, this is what we see in terms of global trends from 1979 up until 2014 in ozone depletion and recovery. Why only to 2014? That's how long the emissions database runs. It's pretty simple. So Camden-Vault is what we call the main run, and that is the blue line. So that's kind of the model's best guess of the truth of what happened. The squared and circle lines are two different long measurement records that we're kind of setting this against. This is showing the total column ozone, which is in Dobson units. It's a measure commonly used in the ozone community, and it's showing the anomaly relative to 1998, which is why they all cross at this point, and why the levels are like 10, 15 Dobson units. The total ozone layer has a thickness of about 300 Dobson units, give or take. So one really cool thing here is that you can see the influence of volcanic eruptions. So this is when Mount El Chichon went off here, and the orange line, which is the run without volcanoes here, you can see starts to depart from the blue line right there. And the gas phase line just shows much less depletion, but particularly in that area as well. You see the same thing happen with Mount Pinatubo, which is an even larger eruption and caused this really kind of steep drop in the early 1990s. So we can look at the trends too, do a linear least squares fit to this data, and we then can just do the same thing for the recovery era, which is defined as post-1999. That's when total chlorine loading in the stratosphere started to go down. So the first thing you notice is that it looks like ozone's kind of starting to go up at the beginning of right after them. And that, okay, I'm running a little short on time, so I'll rush through some of this. But the main takeaway from here is that there is very low stratospheric aerosol in the beginning of this era. There's almost not many, if it's like time, but volcanoes that were going off from like 2000 to 2006, or relative to like the second half of that decade. And post 2005, we had this series of minor and moderate eruptions, which essentially has slowed down ozone recovery. It's a form of natural variability that's superimposed on the anthropogenic ones. So you can see all of these cluster of kind of eruptions that are themselves like an order of magnitude or two smaller than Mount Pinatubo, but especially when taken together, they have a discernible impact. And you can this is just a trend analysis I did using linear least squares fits to this. You can come talk to me about this afterwards if you're interested in the nuts and bolts. You can also say the same signals in vertical and latitudinal trends. You can see how normally we've got a lot of influence from the Antarctic ozone hole down in this southern hemisphere, which is on the left side of the plot. That's the big blue kind of hole in both Camden Vol and Vol Clean. These plots only go down to so this is also only going through 2014 and from 1984 because of the availability of data, so they're not quite as long of trends, but it's kind of very similar to before. You can see these transport of this heterogeneous chemistry influenced air in the gas phase plot, which has much smaller depletion in those years. And then similarly in the recovery era, basically what this shows is that there's very little recovery in the lower stratosphere kind of in a lot of runs. There's more in the upper stratosphere where chlorine is depleting, don't have heterogeneous chemistry, and there's some kind of in the Antarctic ozone region itself. And there's been a lot more studies out on the specifics of how the Antarctic ozone hole is responding to both climate change and decreased anthropogenic signals. And so then, yeah, just in summary, we find that volcanic eruptions deepen the ozone depletion in the depletion era. They have held back the recovery. And the key thing is that we need to represent aerosols and heterogeneous chemistry well when we're looking for this signal, which is seen as such a threshold for the success of the Montreal Protocol that was this landmark international treaty. And that we have to keep in mind that recovery trends are going to emerge faster from the background variability during periods of volcanic quiescence and slower during periods of high volcanic activity. So, thank you all for listening.
Questions for
Yeah, so you're distinguishing between like the effect of different size volcanic eruptions on aerosols, and I was wondering if you're able to distinguish between different eruption types as well, like subduction zone versus hotspot versus other volcanoes have different.
So I am very much not a geologist. I am a volcanologist. I don't know too much about the different types from that perspective. I know you need an eruption that will get it into the stratosphere. You need an explosive type eruption. Unless the eruption plume is over about 12 kilometers is when we consider it to have probably had a stratospheric influence. But if it is in the tropics, then it needs to be even higher. So I don't know if that narrows down the type of volcano.
I'm not even sure if the differences in chemistry would matter for this.
Impacted. Yeah, in general, it's what matters most is volcano size, and after that, it's where it is. So we saw in the diagrams earlier that the stratospheric circulation rises in the tropics and descends in the poles to first order. So tropical volcanoes will have a much larger dual hemisphere signal, and compared to a similar size one that's at a higher latitude.
You mentioned strong non-linear dependencies of the chemical reaction due to temperature
Yes.
in the stratosphere. Is there this is the case that the stratospheric temperature is changing slightly, and so also mediating the ozone recovery just by dynamic climate change rather than just
Yes. Is climate change affecting this, you mean?
Yes, right.
Yes, so the stratosphere as a whole, is cooling slightly, whereas the troposphere is warming due to just radiative equilibrium. So you're seeing a bigger impact in the upper stratosphere, where the gas phase reactions actually have some weaker but reverse dependence on temperature. So a cooler stratosphere slows those gas phase depletion cycles very slightly and speeds up ozone recovery in the upper stratosphere, but the majority of the ozone layer is located in the lower stratosphere, where if you had a discernible temperature trend in a given region, it could slow down the rate of ozone recovery, but ozone itself is such a strong local greenhouse gas that its radiative signal in regions of significant ozone depletion is much, much stronger than climate changes right now.
One last quick question. Yes.
Is there a geographic component? Because like you described that the ozone hole was kind of in a specific location, volcanoes are also in specific locations around the world, so how does that impact of a particular volcano? Is that some kind of component in the model?
Yeah, basically, so truly local volcanoes aren't going to have much of an impact on the stratosphere at all. There's a zonal impact. It's pretty zonally symmetric in terms of like where in the stratospheric circulation can a volcano kind of get its aerosol flung into. There are some like near the tip of South America, for example, that have erupted, and they didn't have much of a global signal, but they were close enough to the Antarctic polar vortex for the aerosols to get in there. So like you can have these other more local circulation patterns in the stratosphere and train these aerosols definitely, but it has to be a stratospheric circulation pattern.